Okay, thanks very much for the invitation to give a talk, and also, of course, to allow me to give it remotely, and in particular for changing the schedule so that it's not too late for me in Germany. So, yeah, I was asked to talk about the PCAC puzzle for the nucleon, axial, and pseudoscalar form factors. So this relates to the reliability of lattice determinations of these form factors, and in particular, as Andre mentioned, the systematic in terms of excited state contamination. Okay, so I think Andrea's motivated lattice studies of these form factors very well in terms of the Monte Carlo event reconstruction for quasi-elastic scattering. Then one needs as input these non-perturbative matrix element relevant for quasi-elastic scattering, and that is characterized by the Pauli and Dirac electromagnetic form factors. These are very well known experimentally, but also it depends on the axial form factor, also not very well known, and this induced pseudoscalar form factor. This is not so relevant because it enters the cross section with a very small factor. So the axial form factor is the most relevant one, and lattice QC provides a very clean way of determining it, of course, via a first principles calculation. So the question really is how, or one question is how reliable are these lattice determinations? Well, as Andre discussed, this depends very much on systematics, so finite lattice spacing, a volume. If you're working at unphysical quark mass, then some extrapolation, excited states, and so on. These must all be under control. And if there are, to see, I mean, how well this is done, it's not always easy. For example, if you're doing a continuum extrapolation, and you just, as Andre discussed, have 3 lattice spacings, it's not always easy to see exactly how well this extrapolation is being controlled. If there are additional checks that we can use, that's obviously very good to see or to demonstrate how reliable the form factors that we extract are. So possible checks that we can impose, of course, in the forward limit, as Andre already presented. We have, I mean, the forward limit of the axial form factor is the axial charge, and as he showed, lattice results now get very reasonable results in terms of these green results here, where the systematics have been assessed to be reasonably under control. Then we get a reasonable agreement with the experimental result for the axial charge. However, at finite q squared, which of course we're interested in for the neutrino oscillation experiments, we can impose the partially conserved axial current relation, which relates the axial induced pseudoscalar and also the pseudoscalar form factor. And this relation must be satisfied in the continuum limit and up to discretization effects on the lattice. And in terms of this pseudoscalar form factor, this is defined through the analogous matrix element as the V minus A1, and just with a pseudoscalar current. And the Lorentz decomposition is very straightforward and just gives you this pseudoscalar form factor. Of course, we don't really have any experimental information on this form factor because it doesn't appear in standard model processes. Okay, so what is this PCAC relation? Of course, it arises out of the axial Ward identity for flavor isovector current. So the derivative of the axial current is equal to the sum of the quark masses times the analogous pseudoscalar current. If we consider other operators, then we can construct correlation functions. And this PCAC relation then, of course, leads to relations between these correlation functions. Here, the example of a 2-point correlation function or a 3-point correlation function, or we can simply sandwich the operator relation between external states and get relations between matrix elements. Of course, trivially, if one performs the spectral decomposition of these correlation functions, then we recover the matrix element relations. And as I said, on the lattice, this PCAC relation should be satisfied up to discretization effects. So if we look at this matrix element here between the proton and the neutron and perform the Lorentz decomposition, then we obtain the PCAC relation between the three form factors. We're taking the isospin limit, so this ML is the light quark mass, so the up and down quark masses are equal. Okay, so in the forward limit, considering this, then we see that the quark mass times the pseudoscalar charge is equal to the nucleon mass times the axial charge, and this is then equal via the Goldberger-Tremaine relation to the pion decay constant times the pion-nucleon coupling plus corrections. If we take the chiral limit, so the light quark mass to 0, then we see that this induced pseudoscalar form factor is proportional to the axial form factor divided by q squared, and this suggests if we go to finite quark mass that this induced pseudoscalar form factor has a pion pole as shown here. This is an approximation, and of course there will be corrections to this. Okay, so just before going on, since the induced pseudoscalar and pseudoscalar form factors are not so often discussed, just to give you an indication of what information we have about them already. Well, in terms of experiment for the induced pseudoscalar form factor, then we have a measurement at the muon capture point in muonic hydrogen. And a recent result from MuCap gives the induced pseudoscalar form factor at this point times the muon mass over twice the nucleon mass to be around 8. And in fact, if one makes some assumptions on the axial form factor and assumes pion pole dominance, then one can actually obtain a result for this GP star consistent with this MuCap result. So pion pole dominance is an approximation, however, it seems to work fairly well. Away from this point, then we can get additional indirect information from pion electroproduction. Here, of course, you have to make some assumptions, so there's some model dependence. And here are some estimates from an early paper. So the induced form factor as a function of the virtuality, and we see a very rapid increase in the form factor reflecting this pion pole dominance. For the pseudoscalar form factor, we can use, again, pion pole dominance and also the PCAC relation. And then, of course, we see that this pseudoscalar form factor also has this pion pole. Okay, so if we want to see if this PCAC relation is satisfied in terms of the lattice data, the first thing to do is to see if it's satisfied on the level of the correlation functions. So going back here, just on the level of these 2-point and 3-point correlation functions. So using these, we can, in both cases, make an estimate of the quark masses by taking ratios of the correlation functions. So one does that in 2 ways. In the first one, using a ratio of pseudoscalar or pion 2-point correlation functions at 0 momentum. And in the second way, using the nucleon 3-point correlation functions, which we will use to extract the form factors. So that gives us a second estimate of the quark mass, and this is evaluated at finite momentum transfer. So if everything is working properly on the lattice, then these two estimates of the quark mass should agree in the continuum limit. So here we have the quark mass is divided by the pion mass squared as a function of the lattice spacing squared. And you can see, obviously, at finite lattice spacing, there's a difference between the two estimates of the quark mass. However, this goes away once you take the continuum limit. So the bottom here, the more precise results are from the pion correlation functions, and the upper ones here are from the nucleon correlation functions, obviously much noisier. But the deviations we see at finite lattice spacing are consistent with being discretization effects, and we get nice consistency in the continuum limit. So at the level of the correlation functions, everything behaves as we would expect. If we then perform a standard analysis to extract matrix elements from these correlation functions, and then we do matrix elements, and then we use the Lorentz decompositions to extract the form factors, and then test the PCAC relation again. And now we look at this ratio rpcc, which is formed such that if the PCAC relation is satisfied, it will equal 1. And we expect, of course, on the lattice, some discretization effects. We see results for this ratio plotted here as a function of the virtuality. On the left here, the pion mass is varied, and the lattice spacing is kept fixed. And on the right, the pion mass is fixed, but the lattice spacing is varied, decreased. And what one can see is that we have a significant violation of the PCAC relation, in particular at low values of Q squared. This discrepancy becomes worse for smaller pion masses and does not improve if you go to smaller lattice spacings. So the violations we see here are not consistent with being due to discretization effects. And of course, in general, we would expect larger discretization effects at larger virtualities here, but we see, in fact, a smaller violation of this PCAC relation. So this is the puzzle referred to in the title of the talk. On the correlation function level, everything works as expected. If we then go ahead and extract our form factors from those correlation functions, then we see significant violations. Okay, and just as an aside, although it's not expected, it's an approximation, we also find that this pion pole dominance, which we test by forming the ratio here in terms of the induced form factor, a pseudoscalar form factor, and the axial form factor, this should be 1 if pion pole dominance is exactly satisfied, but we expect corrections. Here again, we see very large violations of this, in particular at low Q squared. And these violations do not go away as we decrease the pion mass. However, we would expect pion pole dominance to become a better approximation as we decrease the pion mass. Okay. And just to, I've shown these ratios just to give you an idea of what's happening actually on the level of the form factors themselves. We can look at this induced pseudoscalar form factor, here shown as a function of Q squared. And these blue points here are these experimental results for this muon capture, and this point here is from pion electroproduction. And you can see that the lattice results here from a PAX 18 study fall well below these experimental results at low Q squared. However, if you take the lattice results for the axial form factor and pion pole dominance, then you get reasonable agreement. So this violation here that I showed in the ratio is due to the induced form factor, and also, in fact, the pseudoscalar form factor being rather below what one would expect. Okay, so what's the reason for this puzzle? And basically it boils down to problems with dealing with excited state contributions. So Andre already went through the process of, so I'll just very quickly repeat how we extract form factors from our correlation functions. We create a nucleon at some initial time and destroy it at some later time. So this is the 2-point function. With the 3-point function between the source and the sink, we also insert the current. If we do a spectral decomposition of these 2- and 3-point functions, then we don't just get the ground state contribution, we create, of course, all states with the same quantum numbers, so we get a whole series of terms in terms of the 2-point function. And of course, these terms come with an exponential factor of the time times the energy. So then the energy gap is shown here relative to the ground state. And of course, if you go to large times, then these contributions from these higher excited states in principle die away, and you have ground state dominance. But in general, the contribution they make, of course, will depend on the energy gap, and also these overlap factors shown by this coefficient B1 here, which is the overlap of our nucleon interpolator that we use with the excited state. Okay, and then the spectral decomposition for the 3-point function is similar in terms of involving these overlap factors, and of course the energy exponentials of the energies times time differences. But in addition, you also have the matrix elements you're interested in extracting, so the ground state to ground state matrix element, and also for these excited state contributions, we have excited to ground state matrix elements, ground state to excited, and excited to excited matrix elements. Okay. So normally, in terms of how we compute these 3-point functions from which we get the matrix elements, we set the sink momentum to be 0, and then for momentum conservation, the momentum transfer is equal to minus the initial momentum of the nucleon. As Andre discussed, the source-sink separation is normally fixed, and the current insertion is varied, and the computational expense increases with the number of source-sink separations that you calculate. So ideally, of course, for ground state dominance, then we would just choose a very large source-sink separation, but this is difficult to achieve because of this noise to signal ratio growing exponentially. And so for the moderate time separations that we use, we really have to deal with these excited state contributions. In terms of looking at the 3-point functions, normally one constructs ratios with 2-point functions in a way such that in the limit of large times, this ratio would be independent of the separation T and the current insertion tau. And of course, one can construct this ratio for different combinations of the polarization of the nucleon, the current inserted, and also the 3-momentum transfer. So just in terms of illustrating the size of these excited state contributions, what's shown here are 3 combinations for this ratio, sorry, 4 combinations. And as I said, if ground state dominates, then this ratio would be independent of the source-sink separation. There are 4 separations shown here. It's plotted as a function of the current insertion. Then all of these data points here would lie on top of each other, and also the ratio would be completely flat, so independent of the separation and the current insertion. So we see for the first ratio here, which takes the spatial components of the axial current, and it has the spatial component is parallel to the polarization chosen, and the 3 momentum transfer is perpendicular to that. One sees here that we more or less get the ground state dominance that we hope for, in that all the source-sink separations here just lie on top of each other and the ratio is fairly flat. However, if we look at the other combinations where the for example, the spatial component of the current is still parallel to the polarization of the nucleon, but it's also parallel to the 3 momentum transfer, then we can see that we get very different results with the different source-sink separations. This indicates there are large excited state contributions. Obviously, the ratio is not flat, and we see similar behavior for the other 2 ratios. In particular, for this 4th component or time component of the axial current, then we get almost linear behavior here, very different from what we expect. And the yellow bands here are actually what we expect the ground state result to be. We can see it's very far away from the actual data. So you can have very large excited state contributions, and it also depends on what combination of polarization, current, and momentum transfer that you have. So these very large contributions are very well, excited state contributions are very well known. And a way to get around it is to not use all of the data in your analysis. So the most obvious one would be to restrict yourself just to the first ratio, which just depends on the axial form factor that we're primarily interested in. And if we go back to this summary plot that Andre presented in terms of the different calculations that have been performed, then this is the approach taken by some of the groups. So certainly in terms of CalLat, in terms of the MINTS, CLS and PACS results, then they omit this 4th component of the axial current because, again, that really has the largest excited state contribution. And then there are different approaches taken by the NME group, my collaboration, RQCD, and also ETMC. And these other analyses try to take into account more these large excited state contributions. However, what we can see is that there's overall agreement. And this is also an indication that the problem of these excited states is not really one for the axial form factor, but it's more a problem in terms of the induced pseudoscalar and pseudoscalar form factors. Okay, so we have these excited states. What are they? Well, of course, they are resonances, but also they can be multi-particle states. And once you go to pi mass is close to the physical point and you have large lattices to avoid large finite volume effects, then it's these multi-particle states that we expect to be the lowest ones. Thinking of the kinematical setup that we have at the sink, where we have 0 momentum, parity is a good quantum number, and there one would expect the lowest states to be n pi back-to-back, or n nucleon with 2 pions, or at 0 momentum, 3 pions, and so on. Well, at the source where we have finite momentum, parity is not a good quantum number, so one could have either the nucleon or the pion with finite momentum, and so on. To give an idea of the spectrum of states, I've taken a nice plot here from a talk from Jeremy Green. The total momentum is 0, and of course these are non-interacting levels. If you put multiparticle states in a finite volume, then of course the spectrum will be modified, so this is just an indication. And on the left here, we have the spectrum of states as a function of the spatial extent of the lattice, where the pion mass is fixed to the physical point. So if you want to be above m pi L of 4, keep violent volume effects moderate, then you can see one gets a very dense spectrum of states. Similarly, on the right, where the volume is kept, L m pi is kept at 4, but the pion mass is varied, and one can see at heavier pion masses, then we have quite a sparse spectrum, but as you go down towards the physical points, then we have a very dense spectrum of states. So obviously this is not going to be straightforward to deal with, and the problems we're seeing with the form factors are basically difficulties in resolving this excited state spectrum. So the standard approach is to determine, for example, the first excited state or higher states from the 2-point function, because it's statistically more precise than the 3-point function. However, as I said, the contributions here depend on this overlap factor, and we expect that the overlap factor for a single particle nucleon interpolator that we use with the multiparticle states, that this overlap is small. So the contribution of these states to the 2-point function is small. However, the contributions to the 3-point function may be large, because in addition to the overlap factors, we also have these matrix elements, and if these are particularly enhanced, then the contribution here can be significant. And this is basically what we are seeing. So if we look at, this is shown here in this plot where I show the mass gap with the ground state to first excited state shown as a function of the virtuality. Then you can see at the top here, these blue points are the mass gap extracted from the 2-point function. It lies very high, and of course if you have a very excited state mass, that would imply, because of the exponential suppression, fairly small contributions from excited states. However, if we extract the mass gap from the 3-point function, then we get much lower values, and in particular, they are consistent with these multiparticle states that we expect. So n pi back to back when the overall momentum is 0, and nucleon at rest with a pion with momentum at the source. Okay, so these excited states, which are important for the 3-point functions, seem to be these n pi states, and to get more understanding of their contributions, we can appeal, of course, to an effective field theory where the degrees of freedoms are nucleons and pions, and of course that's Baryon chi-pt. And if we just look at a very basic level, just looking at the tree level diagrams within chi-pt, then we have the 4 diagrams shown here. And the first one, which just gives the ground state contribution to the axial form factor, then we just have the nucleon propagating between the source and the sink with a current insertion. While for this second row, here we have a nucleon pion at the source with the pion propagating to the current. Here it's at the sink, and in the middle, this diagram has the nucleon emitting a pion, which then goes to the current. So this middle bottom diagram leads to if we have an axial insertion, leads to the induced pseudoscalar form factor and this pion pole dominance, and also contributes to excited states. And of course, if there's pseudoscalar form current, then it gives the ground state pseudoscalar form factor, etc. And while these other two diagrams here contribute to the excited states. So looking at these diagrams, then it's clear that the excited state contributions come from these transitions, a nucleon to nucleon pi, and nucleon pi to nucleon, whether at the source and the sink. And the energies we expect are in agreement with the ones we found from fitting to the 3-point function. One also finds, as I mentioned before, that the axial form factor is more or less unaffected, and only the induced and pseudoscalar form factors get a contribution at tree level within the chi-PT analysis from excited states. So we get the pattern in terms of where the excited states are contributing, as we've seen in the data. And also we find that these tree level diagrams can account for the magnitude of the excited state contamination observed. So what's shown here are lattice results for the 3-point function, where we take the 4th component of the axial current. And there, these are the data points, and then the line is predicted by this tree level chi-PT, just inputting information on the axial form factor in terms of the axial charge and the pion decay constant. And one can see that the agreement is not perfect, but it reproduces the excited state contamination seen pretty well. So again, this ratio would be flat if there was ground state dominance. And what one finds is that really, as one would expect from this figure, that excited states are really dominating here. So the ground state comes in order m pi over the nucleon mass, while the excited states come in at order 1. And if we also consider the pseudoscalar current, then we can account for these violations seen in this ratio for the PCAC relation. And we also see that, of course, because these excited states here are Paul enhanced, that there's a bigger effect at smaller q squared and at a smaller pion mass. Going beyond this tree level analysis, then a whole tower of n-pi states contribute, and there, of course, one also then gets loop contributions to GA, but these are moderate compared to what we see at tree level for the induced pseudoscalar and pseudoscalar form factors. Although chi-PT provides some guidance, of course, there's limitations on its applicability in terms of small pion masses and moderate virtuality. Also, there are some technical aspects in terms of the spatially extended nucleon interpolators that we use, and also that the source sink separation needs to be reasonably large in order to be, for this chi-PT to be used. As an aside, this lower order chi-PT does not reproduce the excited state contamination seen in the forward limit for the axial form factor, although in principle it's applied at or compared at smaller source sink separations than one should really use. So what we need is really a new approach on the lattice side, and in particular we need to take into account that contributions of excited states from the 3-point function can be much larger than what's seen in the 2-point function. Okay, so I think I'm running out of time, so I will very quickly just mention the works of 3 groups where this has been done. The first, it's my own collaboration. There we've done an analysis where we extract the form factors from the correlation functions using all available information in terms of all components of the axial current and also the pseudoscalar current. And as shown before, this then gives these yellow bands that are indicated in these figures. And there we do an analysis, including, of course, the ground state. We put in the NPi contributions and include some constraints from this tree-level chi-pt analysis, and also account for a possible additional excited state. And then if we look at this rpcc ratio, then we get results now which are much closer to 1, and the deviations we see are consistent with the size we would expect from discretization effects. And also, although not required, we also see an improvement in terms of this consistency with pi and pole dominance. Another group, PDME, they have done a slightly different analysis. They've fixed excited state energies from the fourth component of the axial current in terms of the 3-point function, and then they use this for the analysis of the other 3-point functions. They find energy gaps very similar to the ones that we see, consistent with the chi-pt expectation, and they again see a very similar improvement in this in terms of reducing the violations of the PCAC relation and improved consistency with this pi and pole dominance. Similar work has also been done by the NME collaboration. I just also want to mention the work of ETMC. They do a very similar analysis to what has been done by PDME. And again, in terms of the excited states extracted from these 3-point functions, they see, again, very similar energies. However, for the PCAC ratio, then they still see significant violations, although these violations do decrease as you go towards the continuum limit. And certainly the extrapolation, this is very preliminary, this is just taken from a talk of Dina Alexandru from the KITP program of a couple of weeks ago. Then they do seem to get consistency in the continuum limit. So obviously this is different to what was observed by other groups. Discretization effects weren't responsible for this violation in other works. However, for twisted mass fermions, the situation is slightly different in that one has Isospin and parity violation at order a squared, and perhaps this is responsible for this different behavior here. But nonetheless, one can see that, as I said, they get consistency in the continuum limit. So since I've gone, I think, quite over time, I will skip the mention of the QCD results. If someone can ask me about that in the during the questions. And so just to summarize, then lattice QCD, of course, can provide, in principle, a very reliable determination of the axial form factor. As you saw, there are many new lattice studies of the axial form factor, and of course the focus is on increasing precision and controlling all the main systematics. Constraints such as the PCAC relation on the form factors provide important checks. The puzzle that we saw very large violations seen when using traditional analysis techniques seems to be largely resolved, and certainly the source of the violation seems to be these very significant excited state contributions, in particular from NPi states. And from leading order chi-pt and also the data, we see that it's really the induced pseudoscalar and pseudoscalar form factors which are most affected. Well, one would say that the excited state contamination for the axial form factor is relatively moderate in comparison. However, that doesn't mean that it is easy to deal with. The size of the excited state contamination will depend on many details of the analysis. the choice of nucleon interpolator, source sink separations, of course the pion mass and the spatial extent of the lattice in terms of the spectrum of excited states that you get. And all, I mean, the analysis, as Andre also emphasized, needs to be done very carefully in order to obtain precision results. And certainly this is being attempted in the current studies, as we saw the very nice agreement amongst the recent results for the axial form factor. But with these new approaches, where one takes into account that the excited state contributions to the 3-point function can be very different to the 2-point function, then we find that the PCAC relation is satisfied in the continuum limit. And what one can also see, unfortunately I didn't show you, is that lattice results for the induced pseudoscalar form factor now reproduce this mu cap results at the muon capture point. And we also find that pion pole dominance is held to a few percent. Okay, then I stop there, and thank you very much.
Thank you so much, Sara. Are there any questions?
You want to show us your result?
Yeah, great. Thanks very much. Yeah, so these were generated on the CLS ensembles. So Konstantin will present results on a subset of these ensembles from Mainz. So I won't say very much other than we aim for high statistics. We have 5 lattice spacings, reasonably large volumes, and quark masses going down to the physical point. So we aim to control all the main systematics. One feature of these ensembles that we do exploit is that we have 3 trajectories in the quark mass plane. So here is a combination proportional to light quark mass, here one for the combination proportional to the strange. So we have 2 trajectories going to the physical point and 1 going down to the chiral limit. So this enables a very good control of the quark mass plane and any extrapolations we make. If we just calculate something simple like the baryon mass spectrum, then you can see we get very reasonable agreement with experiment, in particular for the nucleon mass where it's expected. We're a little bit above, possibly for these lower decuplet masses, but again, we're not doing a proper resonance treatment of these states. So in terms of the baryon spectrum, this is reasonably well reproduced. Our dispersion relation is reasonable in terms of agreeing with the continuum limit. And yeah, maybe I just come to the results then for the axial form factor and the induced pseudoscalar form factor. We use 2 different parameterizations for the dependence on Q squared, dipole, or the Z expansion. We get reasonable agreement in the range of Q squared from 0.2 up to 1 GV squared. There's more of a difference at low Q squared in that we get a lot of parameterization dependence when we try and extract the slope, so the axial radius, but this is probably due to the lack of data we have in this region. But this is perhaps not such an interesting region for thinking of long baseline neutrino oscillation experiments. So we get a nice agreement between the different parameterizations, and we also, as you can see, reproduce this GP star for this muon capture point. Okay.
Thank you so much, Sara. Is there any urgent question?
From the point of view of neutrinos, let's focus on GA, since this is what is the most impactful thing, as you said, for the cross-section. Yep. Mm-hmm. When you do the subtraction of the excited state, you emphasize that the effect on GA is small, but it is a loop effect. And so I was wondering if there is a physical estimate for what that effect should be, right? Because we are looking at numerical results, and I wonder if it agrees with the estimate of this loop effect.
Right. So, I mean, of course, it depends a bit on the details of the analysis, but estimates here from, for example, Oliver Baer, estimate, I mean, they have that the effect on the axial form factor is more or less independent of Q squared, so these loop effects, and is around, for example, 5% or so. So this, again, these comparisons are rather qualitative because of the limitations on the applicability of this chi-PT. But one expects at least a few percent, but it will depend very much on the details of your analysis, which is not really what chi-PT is sensitive to. So, for example, up here, you can see that, well, I mentioned that excited state contamination is very low here, where we're extracting GA. But of course, if you use much smaller source sink separations, then you will see some excited state contamination. So it depends very much on the details of your analysis and what you are focusing on. So, for example, Andre showed plots of 10, for example, source sink separations, some of them very small, and taking that approach may be useful in terms of really teasing out more than one excited state. But in terms of these estimates from chi-PT, then I think they're around the order of 5%. But again, it depends on the source sink separation and other details. Is that answering your question?
Maybe we can continue this during the discussion because we are running over time.
Okay.
Thank you so much. Let's thank Sara and Andre. And take 25 minutes of coffee break.